We're ready. Okay, so welcome everybody to this new session of the Themeless Seminar course. Today is the first session of the year, and we're very pleased to have with us Professor Santiago Badia. Santiago is a professor at computational mathematics at Monash University, Melbourne, Australia, and previously he worked at the Applied Mathematics departments at Politecnico de Milano in 2006 and Sandia National Labs, New Mexico, USA, in 2007. He joined UPC in 2009, where he was appointed Professor of Computational Science in 2017. He obtained his PhD at UPC in 2006. He has received several prizes for his research. I'm not going to go through all of them, but he has made numerous contributions on stabilized finite element methods and feature or embedded finite element methods, large-scale parallel domain decomposition solvers, and coupling techniques. He also promotes and leads novel open source scientific software projects like Badia. Today, Santiago is going to talk us about recent advances in unfitted finite element methods. Please.
So thank you. It's a pleasure to be here again after almost 3 years. I was telling that, because the last time I came here was in January 2020, but then right after that, with all the COVID thing, Australia decided to lock up the border. So I've been locked in Australia for 3 years. It's not that bad because the country is pretty big. I didn't feel claustrophobic, but anyway, I couldn't come to Barcelona for that long. So now I'm again here 3 years later, and I was asked to talk for about 50 minutes, and I decided to talk probably one of the things in which I've been working the most, so I will be able to fill these 50 minutes with my work. And I'm going to talk about unfitted finite element methods, why we started working on that, and what we have done on this in order to improve the situation of these schemes. And many of the things that I'm going to present today have been done in collaboration with lots of people, as you can see here: Alberto Martin, who is now at ANU in Canberra; Francesc Verdugo, who is now a lecturer at the University of Amsterdam; Eric Neiva, who is at Sorbonne University in Paris; Peter Martorell, who is a PhD student here at UBC; and Ridja, which is another student I have at Monash. So hopefully it works because we had some technical issues before. Okay. So just very simple. Here I'm going to be interested in methods, in unfitted finite element methods that are C0 continuous, okay? Standard nodal Lagrangian finite elements. And there are so many names to talk about this kind of algorithms. They have so many names. I'm not going to get into that. But probably, XFEM is probably the starting point of the kind of methods I'm interested in. Then you have all these CAT-FEM type approaches that have cost penalties that I will talk about. Other people use the finite element method. We propose to use segregation techniques, etc., etc. There are lots of works on these kind of methods. And the main idea, as you probably know, is that what we want to do is to get rid of structure mesh generation, where you have to deal with complex geometries. And instead of that, we would like to have our mesh or some kind of background mesh for which we can use whatever we like. And in that sense, it probably makes some sense to use some kind of structure meshes. And then let's say, when we create our background mesh, forget about the geometry. So we have much more flexibility. So it looks good, but then the problem is, then some of the problems will arise, and we'll discuss them later on. So the first reason is why we want to go from here to here. And I'm going to give a little bit of motivation why we started this work. Probably the main reason is that when you go to, let's say, somehow larger scales, the creation of the computation of these unstructured meshes is quite hard, right? It's a very non-automatic process that requires lots of human intervention. And then there is also very strong coupling between the geometrical discretization and the functional discretization of your elements. For instance, when you want to create a mesh that describes a given geometry, then that mesh is going to have an effect on the numerical result that you're going to get, for instance, through the shape ratio of the elements, right? So another very big problem is that when you go to somehow larger scales, when you have unstructured meshes, you are required to partition these meshes into pieces in order to be able to run them in parallel to exploit distributed memory machines. And nowadays, that partition is made through graph partitioning approaches. And parallel graph partition is quite a big problem, quite a bottleneck, right? You can use Prometheus, etc. But if you have used that, you know that the computational requirements are huge. So, and even worse if you think about adaptive refinement and you want, for instance, dynamic load balancing. Another problem is that we would like to have a much better interaction between geometry and numerical computations. We would like to have in control of everything, not just receive a mesh, but start working on the CAD representation within our code. So based on these motivations, we started working on this. For instance, one of the things that we wanted to get at some point was the ability to solve problems in non-obvious domains using octree meshes. And why this? Because these kind of octree meshes are very, very easy to generate, and they are very easy to compute in parallel, and they are very easy to distribute in a dynamic way if you like, because they rely on what we call space filling curves, which let's say is like moving across all the, or we create a curve that goes through all the elements. So at the end of the day, my problem is a 1D problem that they have to partition, and for that we have excellent libraries that do that on hundreds and millions of processors. Right? So we want to exploit that. That's something that everybody uses, for instance, in astrophysics and geophysics applications in which they work on spheres or very simple geometries and they don't care about complex geometries, but we would like to be able to use that for more complicated geometries. Other things that why we were interested in this is the ability to have moving interfaces in space and time. Space and time start being something that you can start thinking of. The space-time and structured meshes seems to be quite impossible, right? And also at the linear solver step, you know, algebraic multigrid methods are a little bit hard to make them work sometimes. They require lots of ad hoc tuning. And if you are able to use geometric multigrid, that would be excellent. But for structural mesh generation, that's quite a problem because the coarsening strategies is not going to work there. So what we would like to do is also at the end to be able to use geometric multigrid method, even if you're dealing with complex geometries, right? So this is more or less our motivation. And now I will start talking about also which are the problems of these approaches, right? One of the problems is that these methods in general are not that popular because of robustness. They have some issues that you have to deal with in terms of stability and ill condition of the linear system that derives out of this discretization. The other obvious thing is that then you will need to integrate on CAD cells, and that's something that from a geometrical point of view is not that simple. I will slightly talk about it today if I have some time. And then the other thing that you have to deal with the boundary conditions somehow because they are not fitted. So the strong imposition of boundary conditions that you can do in a standard body fitted FEM is not going to work here. In that sense, we are not going to do anything special. We're going to use niche kind of methods, and for us, this is doing what we want. So I go slowly. I just start talking a little bit about what I would do in a naive approach to unfitted methods. So I would have here my mesh, my background mesh. I would have here, let's say this is the interior of my domain. I would classify my cells into interior cells and CAD cells. All the cells that are outside, we don't care about them. We can forget about these other cells. And here what we have is what we call an active mesh, right? These are the cells. These two set of cells are the ones that define the active mesh or the active domain. Okay, so now you can put your preferred finite element discretization on that mesh. You can do that. And then the only issue that you will need to deal with if you want to use an unfitted finite element method is to being able to integrate in the interior of these CAD cells. Let's assume that we can do that. And you can just, doing that, you can just solve your problem. This is the weak form of the problem. Let's assume that you are using Galerkin. So you're using this active finite element space for the test and the trial functions. You solve for your problem and you get a solution. So this is, let's say, some kind of XFEM approach. But as we will see, this has many issues, right? And for instance, we are going to use, this is not totally well focused anyway. So we are going to use niche type methods. And you can see here that, for instance, this is for Poisson, this is for linear elasticity. If you haven't seen these niche methods before, what we do is, so we have the Galerkin terms that come from the Poisson equation, and then you have additional terms in order to enforce the boundary conditions. For instance, if you want your solution to be equal to G on the Dirichlet boundary, you will add this kind of penalty term, right, that once this to be equal to this. And then you have these additional terms that come from consistency after integration by parts. And then you have also this additional term here that is introduced in order to keep the symmetry of your problem in case you have any symmetry there, and to keep a joint consistency. So this is the Nietzsche method. This tau is the penalty parameter that you have to pick. And for linear elasticity, pretty much the same, right? You will need to add these terms. You will have the fluxes and this additional term in order to pick joint consistency. So this is the problem that we want to solve on that mesh. And with that, we would be able to start working with unfitted finite elements. But unfortunately, this is not enough, okay? Because just to give you an idea, this method in general is not going to be stable. Because with Nietzsche methods, you have these terms. This is what you spoke. You have these terms that have no sign. They don't provide the stability. So you need to absorb them with a part that provides stability, right? And the way we do that in body fitted finite elements is through what we call trace inequalities. We are able to bound the L2 norm on the boundary of our cells, of our functions, with respect to values, let's say in the interior, norms in the interior, right? We bound the values on the boundary with norms in the interior. And doing that, we can now bound this term in terms of this term and the one that comes from the learning. Okay? And this way we can prove that the Nietzsche method is stable for tau large enough, and this large enough can be quantified. You can use local eigenvalue solvers in order to quantify which is the value of tau that you need, but we have rules of thumb in order to decide which is the value of this tau and have stable methods. However, when we go to unfitted finite elements, the situation is not like this anymore, and you can just find a counterexample. For instance, if you think about this cat cell here, and you believe that this is going to be true, you realize that that's impossible, because when this goes to zero, this part here goes to zero, while this part remains constant, right? So the constant that you're going to have here in this inequality is not going to be uniform with respect to small cat cells. So this is going to blow up in this epsilon here. And that's something that we suffer when we try to work with naive, let's say, unfitted finite elements, because we have no stability. Okay, the tau that you will require goes to infinity, everything breaks down, and it doesn't work. So we need to solve this issue. Okay, so you could tell me that don't use Nietzsche, use the standard penalty method, then you have a consistency error, you cannot go high in order, or you could use a non-symmetric version, but in this case you don't have a consistency. You cannot use duality arguments, and then that's also something that is going to be problematic in terms of accuracy. And even if you solve this, you still have another problem, and the other problem is condition. Even if you have a stability with these methods, the next issue is the condition number that you get when you try to solve your system. And again, that's pretty easy to understand. In finite elements, we know that the condition number of our matrices go with h minus 2, where h is the characteristic size, let's say, of our finite elements. This comes from an inverse inequality. And when you go to unfitted finite elements, you can prove that the condition number blows up with the ratio between the volume of your cell and the part of your cell that's inside the domain. So if you don't control where the cats are, this can easily go to zero, and then you end up with a singular system. And that can be the case for sure when you work with unfitted finite elements, because you cannot control where is going to be the cat located. Okay, so yeah, this result, as I said before, relies on an inverse inequality and some kind of a result like this, in which we say that the L2 norm of our function is bounded above and below, but the Euclidean norm times h to the dimension of our set. Okay, so we need something like that, and a discrete inverse inequality to have this kind of results. But this is not holding in the case of unfitted finite elements. So these are the two main problems that we have: the lack of stability when we use Nietzsche type terms, and even if we use penalty terms or non-symmetric versions, we always end up with the condition number that can go to zero. So how can we solve this problem? One of the techniques that we can consider what they call ghost penalty methods that were originally proposed, let's say, by Burman in around 2010. And the idea is, okay, it's obvious from the previous discussion that all the problems are going to be due to the cat cells. So we need to do something there. We need to add some kind of a stabilization of these cells in order to solve that problem. Okay, so we need to design a term that we are going to add to our problem. Again, these are the spaces, the finite element spaces, standard finite element spaces on this mesh with these two sets of cells. But we're going to add here a term, a stabilization term, that requires to have to enjoy some properties. From an, let's say, quite abstract point of view, the idea is that we need to add something. I put here this for the Poisson equation, but you could do something similar to elasticity or other problems. We need to add something that extends the stability that you have from the lurking, which is only in the interior of the domain, to the whole active mesh. So the stability that's not only in the interior part, but also in the external part of the cat cells. If you're able to have something like this, then you will be able to solve the problem that we had before. So you need to extend the stability that you had before, adding this additional stabilization. This is one of the requirements of the stabilization term that we need to add in order to solve our problems. And then this is somehow a standard continuity. It has to be continuous with respect to the right norms. And then you also need some kind of weak consistency. What you add here, it doesn't have to be consistent, but at least it needs to go to 0 with the right exponent of h in order to keep the error estimate that you have in your formula. Okay, so these are the main requirements for the stabilization term that they want to design. And Burman proposed some stabilization that enjoy these properties in 2010, and he called them ghost penalty methods. And one of them is the one that I show here. And what he did was the following. He proposes to identify all the faces in our mesh that are in contact with cat cells, okay, which are the ones that I put here in blue. And on these faces, he proposes to penalize with some h raised to some specific power. K is the order of approximation of our finite elements. He proposes to penalize the derivatives, normal derivatives across these faces of our solution. Okay, so you see here that we have a penalty term. And let's say for linear elements, in general, on these faces, you have two-shape functions, you can have kinks here, but what he proposes is to penalize it in such a way that somehow you have an extension, right? You don't allow that kink on the face. Okay, so this is the idea. You can see that doing that, you are somehow creating some stiffness here, and then somehow you expect to solve the problems that we were discussing before. If you have any question, please stop at any, let me know, and I can try to answer. Another thing that you can do, probably he didn't show it this way in his original article, but I think that he was talking more about like a two-level approach in which you have macro elements, and in which at the macro element level, your elements have enough portion inside. They didn't have the issue related to the small cat cell problem. And what he was proposing is, okay, if you have your solution, let's penalize the distance between your solution in this macro element with a polynomial of your given order in that macro element. What he's telling me is that if you're in a macro element in which you have this kind of flexibility, at the end of the day, you are just saying, okay, I want it to be, let's say P1. I want to penalize the distance between our finite element function and a function that is P1 in the whole macro element. So again, you are introducing some kind of rigidization, stiffness on the boundary, and this way you can prove with this term that you satisfy all the properties that I told you before. So in this article, you can find all the analysis. He added these terms. He proved all the results before, and also proved that with this basis, you can have a condition number that is analogous to the one that you have with standard finite elements. Okay, so with this, you can start having good results when you use some finite elements. It has a couple of issues. The first one is the choice of the penalty parameter that you have to add in any case here. And the problem, you can probably see that easier here, is that when this is equal to 0, certainly you're going to have an issue because you have no stability. We have the problem that I told you before. When this is very large, you also are going to have problems because this is too much. If you start trying to make you know, that you continue your normal components of derivatives across all these phases, when you are trying to enforce, when this coefficient goes to infinity, you end up, let's say, with a huge element that is of the size of your domain. So it's a little bit problematic because you have a method in which in the two limits, when it goes to zero, when it's very large, it's going to break down. Okay, so that's one of the issues of these kind of methods, as we will see from our numerical experiments. And the other one is that they are adding, at the end of the day, some kind of artificial diffusion, and probably in some cases you don't want to do that, or you're not interested in this. What we proposed was slightly different. What we proposed in 2018 was to create some kind of extension operator. So the idea was in this article was, okay, let's get our finite element space only in the yellow region, in the inside, try to extend it to the cat cells, but let's eliminate all the degrees of freedom that are involved. Okay, so that's what we proposed in 2018. So, and I have to say that this is something that's obvious in VG, because in this continuous collaborative method, you can have a polytopic mesh and nothing changes, let's say. So for VG, there is not any issue. When you go to CG, things, as we will see, are slightly more involved, because you need to enforce continuity across these weird, let's say, aggregates that can have somehow arbitrary shapes. Okay, so we can also think which are the properties that we require for this extension operator that takes finite element functions defined in the interior and extend them to the cat cells. And it's very similar to what we need when we have stabilizations. We need to be able to prove that the norm of the extended function in the active mesh is bounded by the norm of the function in the interior, right? In the interior domain. And the same for L2 and H1 norms. If we have this, that's the first thing that we need. The other thing that we need is approximability, because now the image of this operator is not the active finite element space on the whole, let's say, active mesh. It's less than that, right? Because we are only consider a subspace of this. The image of the extension of the interior functions does not cover the whole active finite element space. So it's not straightforward to prove that with this we have enough in order to get the desired approximability properties of our finite element space. But okay, we were able to prove this. The analysis was here, and we're able to prove that with this approach, in which you can see that what we do here is we don't add anything to the problem, it's still alerting. What we did was to modify the spaces. Okay, with this we're able to prove stability, error estimates, and condition number bounds that are the same as the ones we would get with the body-fitted finite elements. Okay, we also extended all this machinery to indefinite problems. In this work here, we did it for a mixed finite elements or Stokes problem, and we're able to prove that you can also get in subconditions when you have this kind of propagation spaces for velocities and pressures. So in order to create these discrete extension operators, it's quite simple. What we did is a simple algorithm in which we touch the interior cells, and then we go through the cat cells, and we try to find which is the closest touch cell by phase, and then we aggregate them to them. If some of them have not been touched, have not been aggregated yet, we proceed again. Still, we end up with an aggregated mesh. Okay, so that part is very simple. When we have this, now on the interface between aggregates, we have degrees of freedom, and then we need to define the concept of ownership. It's arbitrary, to one of the sides. Okay, so every degree of freedom that was, for instance, this is for linear finite elements. You can do the same for high order finite elements. The ones that are on the interface need to be, we need to give them the concept of an owner. And when we do this, now what we have to do is to constrain these degrees of freedom by the values in the interior cell. Okay, and we do that through some kind of extension, and that's very similar to the kind of constraints that you have in adaptive mesh refinement. I would say that it's even slightly easier because it's cell-wise. Okay, so with this, we're able to define constraints of these values with respect to the interior cell in each aggregate. I think that I didn't say that, but in the previous algorithm, each aggregate only has one integer cell by definition. Okay, so for each of the aggregates, there is only one integer cell that extends to the whole aggregate.
What happens if you have a concave, I don't know, I mean, like the tip of an airfoil, or
You do the same and you end up with a mesh, and then you do the same procedure.
you have to walk many elements to do this.
No, you can prove that this is bounded. And okay, if you have something like this, you have a, let's say, if you have like something that is extremely thin, then you are gonna, and you cannot capture it with your mesh, we cannot do magic. If you have something that's extremely thin and you cannot capture with your mesh, that's gonna be.
But what do you do as compact solution? That's what I'm asking.
It's gonna create an aggregate that probably is gonna be. It's gonna not take into account that shape in an accurate way.
You cannot represent that shape, but at a certain point you need to.
Yeah, you can do that. You can use this. You will see that we have done that for many complex geometries that can be non-convex, and it works. Okay. There is not any limitation in that direction. But again, we cannot do magic. The same as with Gauss penalty. If you just have these kind of weird spikes and you don't want to capture them with your mesh, you need to decide whether these geometrical details are interesting or not for you, and if you want to capture them, you will need to capture them with your mesh too.
But I think that what we have is thinking is that then you have one interior in one direction, so you have one direction of the gradient, but not on the other side. So how you manage to keep it there?
If you have something like this and you don't have anything to capture that, let's say if you want, the problem I think is that you want to capture geometries that are the subgrid are so small, let's say are order epsilon, but you want to have a condition number that's order h. That's impossible because you are not representing that with your geometry. You need to decide whether you want to capture these geometries or not. We can discuss that later if you want with okay, so when you do these kind of things, you can see that you solve the issue related to the condition number. Because, for instance, here what I'm doing, I move in a circle, and I see which is the condition number that I get if I don't do anything. You can see that the condition numbers are pretty much rubbish. The same for 3D. If you don't do anything, the condition numbers are so large, probably unreliable. And when you do aggregation, you solve the issue related to the condition number. Sorry again. You see the right condition, the right convergent results. We expect it from our theoretical analysis, and then we can apply this to different geometries. And here, the good thing is that we went to parallel. We use standard solvers. I don't have to do anything special with algebra and multigrid. I use standard solvers for this kind of algorithms, and we get good results similar to the ones that we get with body-fitted meshes. All the scales, all the computations in these algorithms are scalable, and this is the number of iterations of the algebra multigrid method in PETSI. You can see some degradation here in the linear solver setup, but this kind of degradation is also very similar, pretty much the same as you have in body-fitted meshes. This is something related to the scalability of the PETSI AMG solver. Now, let me talk a little bit about the link between these two approaches, between stabilization or changing the finite element spaces. And then you can see that they are pretty much linked. And this is what we proposed recently in this article last year, in which what we propose is to solve the issue that we observed in standard CAD-FEM algorithms, right? This kind of logging. And what we propose here is quite natural, right? Let's say, okay, I know that in this space everything works. I know that in this space we have some issues. Let's penalize the distance between these two spaces, which is just to add some kind of penalty on the CAD cells. You can use an L2 penalty with the right h-2 here, or you could use an h1 penalty. You can do the analysis and you can prove the same results that we required at the beginning of the talk for cost penalty methods. Okay, so this is what we call a weak ACFEM algorithm. And then we started comparing the different algorithms. Here, this is the phase-based Gauss penalty that I introduced before, in which you add you penalize the normal component of derivatives. This is the one that's based on aggregates that I also introduced before. And these are the weak versions of ACFEM. I'm not going to talk about this one. We don't care about this one. With regard to the finite element spaces, since all these methods here are adding a stabilization, that they are working with the original finite element space in the active method. While the last one is the strong ACFEM method, in which we have no stabilization, but we solve our problem in a subspace of this one, okay, for which we know that we have the required properties, these extensions. So here I'm going to use Poisson and linear elasticity for two different analytical solutions, and to the 3D linear and quadratic finite elements. Okay, we play with all these possible choices, and overall, what we can observe, this is the errors in L2 and H1 norm, and you can see that if you use standard methods and you play with the penalty, you can see weird stuff, right? If it's very small, the errors are very large. If you increase it, you see this stiffness that I told you before, and then you completely lose accuracy with the standard CAD-FEM methods. While if you use the method that we propose, the weak version of the method that we propose, we get much better results. This line here is the strong ACFEM. Since this one has no stability, it does not depend on this coefficient, so it's just, it's constant. Yeah, for the condition number, something similar, but I would say that this is something that you would expect. This part here is because when this goes to 0, you have the small cat cell problem, and the value that you will get here will depend on how small is the smallest cell in your mesh. And this part here is something expected because as you increase gamma, the condition number is going to increase linearly. So that part was expected. These are convergent results, probably not that easy to see, but you can see that with the weak forms, we get much better results than with the strong forms, and much better to see probably here for linear elasticity in 3 dimensions. You can see that the condition numbers of these CAD-FEM methods is much worse than the ones that have this weak ACFEM approach. So we would say that this makes these methods much less insensitive to the penalty terms that to the numerical coefficient that you have to choose when you put the penalty. Okay, but at the end of the day, you see that with these methods, the limit of this weak version converts to the strong version that you originally proposed. What else we did? Okay, we have been working a little bit on fixing these problems for some time. Then we also wanted to apply to extend, let's say, the applicability of these methods. And one thing that you can tell me, and somehow it's related to the comment by Ricardo, is that when you start aggregating things, or when you start adding all this stiffness on the boundary, you are somehow coarsening the mesh on the boundary, right? I always say that we cannot do magic. If you have a spike that we cannot capture with the mesh, that's our decision whether we want to pay the price or not for that. But we can also bound the size of these aggregates based on some geometrical properties. But in any case, it's interesting to have the ability to have adaptive mesh refinement. One, because we want adaptive mesh refinement for multi-scale problems, right? And second, because we probably want adaptive mesh refinement in order to, let's say, be more refined on the interfaces related to these aggregations, etc. So it's not that obvious how to extend all this machinery to adaptive finite elements, because now we have 2 sets of constraints. The ones from these extension operators, and then the ones from adaptivity, which are the typical ones that you probably know related to hanging nodes, right? When we want to enforce continuity using nodal Lagrangian finite elements, we need to have some kind of constraints on the hanging nodes, okay? And the mix of these two is not that simple. So I'm not going to get into details there, but the key idea is how we define what is well posed and what is ill posed in order to satisfy all the robustness properties that we had before, but still being able to solve these problems on all these constraints, these 2 sets of constraints. So the main idea here is that there are nodes that only belong, let's say, to CAD cells, but are also constraining hanging nodes that are well posed because they are on interior cells. So we can check mathematically that these are not going to affect our condition number of our stability because they are already well posed, because since they constrain this one, they already have support in a whole small cell. Okay, so this way, if we consider these kind of nodes as well posed, we can prove that we can solve all constraints locally, which is the key here. We can have all constraints and solve them locally. right? We don't have cycles or something that we cannot. We would require like global computation. This is not the case here. Everything can be solved locally, and we can start using these kind of extension operators for adaptive mesh refinement. Okay, we have a work with all the details here. There are lots of details. This is just when you go to parallel, it's not that simple, but yeah, we did that work, and then we are able now to solve problems with adaptive mesh refinement. And you can see here that you do certainly an improvement with respect to uniform refinement. So, and this is also the same for weak scalability analysis. All the steps now we have adaptive mesh refinement here, and the key, and that's something that's completely different to what we have with body fitted meshes, is that the mesh partitioning and the dynamic load balancing is extremely scalable because we are using OC3 handlers that are extremely scalable. It's impossible to think about doing something like that with body fitted meshes because we would end up all the time with a graph partitioner that would destroy all scalability. So we can also extend that to interfaces. That's going to be very simple. The only thing that we need to do is do the same for each domain. So when we have multiple domains that are interacting, we are going to use, let's say, an Nietzsche type enforcement of traces. And in each of these domains, we're going to use this discrete extension operator independent. Okay. And with that, right, that simple idea and a Cartesian plot of these spaces, we have a method that is robust with respect to cat locations and also can deal with the interfaces. And we did that in a work that I don't have it here anyway. And we also consider the case in which you have huge jumps of physical parameters in linear elasticity, and that's something that's we used. It would say that this is not new from in literature, but using the right averages on the interface because you have values that are completely different and certainly not well defined on that interface. Using the right average, you are able to end up with methods that are robust also with respect to jumps in terms of with respect to the jumps in the physical coefficients. And this is what we did. We did analysis and all the work for interfaces is here in 2021. And now we're able to solve problems in which we have, let's say, a domain in this cube, and we have a matrix that has a completely different, some orders of magnitude different physical properties. And we can see that the error is the one that we would expect. And also very important, the condition numbers are quite independent on cat cell locations and the jump on the jump of the physical parameters. They are pretty much constant. If you try to do this in other cases, you would see huge changes here. So yeah, this is also weaker scaling. Again, very good weaker scaling also when you have interfaces, but not everything is so good because then you go to high order methods. First and second order work well, but we somehow knew that at the very beginning because you know that interpolation is good, but extrapolation is bad, right? And somehow we are extrapolating here. So we say, okay, probably for linears and quadratics that's going to work, but impossible that you go to high order, something is going to break down. And this is what happens if we try to solve now a problem. This square embedded in this mesh, and you try to solve here. I don't remember what problem was that, but probably some dirichlet and then boundary conditions on the boundary. You start increasing the order. For linear and for quadratic, everything works really well. In 2 dimensions, it's hard to break down a third order. Third order works pretty well too. But when you go to 4th or 5th order, we start having issues. And the issues are not, let's say, related to the formulation somehow. With exact algebra, everything should work. But the problem is related to the propagation of rounding errors. Okay, when you compute the constraints, because they are based on extensions, and then you have propagation. The method is not really stable with respect to the propagation of rounding errors. When you go, this is also for 2D, similar. You can solve 2, 3, 1, 2, 3, 4, a couple of points. 5th order, only 1. In the other cases, our multi-bit solver wrote down. In 3D, it's even worse. You can do very well 1 and 2nd order, 1st and 2nd order. For 3rd order, in some cases, it doesn't work. So now the question that we try to solve here, by recent work, is how we can solve this ill conditioning, this lack of robustness when we want to go to high order finite elements combined with unfitted. And First, what's the reason? I already told you more or less what the problem, and how to design a better behaved high-order scheme, high-order discrete extension operator. Right? So so far, we have been using all the time Lagrangian basis, and what we can prove is that this discrete extension operator, the module of this operator goes with something like this. When this is somehow tells me how many how many sizes of my element I am extrapolating the values when I have cat cells. Right? This is a measure of the extrapolation distance raised to k, which is the order of approximation, first, second, third order finite elements, and the dimension of our problem, the space dimension. Okay, so you can expect here to have a problem, and that's going to be much worse when k increases, right? Because it's the exponent. So this is for second order. This is my finite element. Let's assume that I want to extend it here. I don't know what it is. Let me extend this, increase the extrapolation distance. You can see that the numbers are increasing. For second order, that's not that bad. We will never do that in general because most of the cases our extrapolation is going to be very small. All the time in this talk, to simplify things, I'm telling you that a cat cell is a bad cell. That's not really like that. In our codes, a cat cell, we can be much more relaxed and only flag a cell as bad when it has a very, very small portion inside the domain. Okay, so in general, we never do these extrapolations. But in any case, we wanted to check what works here. For second order, it's not that bad. Let's put fourth order, and here the extrapolation, you have numbers that are huge, and that's going to affect all the numerical computations. Here we have the conditioning of this discrete extension operator with respect to the extrapolation distance. Again, this is just to check. We never go through that. But with respect to the order, you can see that this huge degradation of the condition number. And our goal was to define a stability constant and condition number that don't grow exponentially with the order of approximation if our higher dimensional space. Okay, so somehow the message is that we don't want to extrapolate inside the domain. Our integrals are always inside. We never integrate outside in our, let's say, ACFEM type of method. So our main motivation here is not extrapolate inside the domain, because if we start extrapolating, we start playing with these huge numbers and something, and then we're going to end up with problems. So what we are going to do is we use a model basis. We're going to look at the model basis, model C01D polynomial basis here, and you can see that the first two are the standard linear basis functions, and then the higher order ones, let's say in 1D, are like bubbles, right? They are sit on the boundary, and they depend on what they are called these Jacobi polynomials that we have here. Okay, so that was the starting point of our motivation to solve the problem, because what we propose, okay, certainly you can go to multiple dimensions by tensor product, and it's very easy to enforce continuity because you have the vertex shape functions, edge shape functions, face shape functions, and then with the standard local to global in our codes, we can preserve continuity globally in these finite element spaces. So it's very easy to enforce continuity. So what we can do here, our idea is, this is for the bubbles, let's say in 1D, which is ordered to up to k, the one that you want to choose. And we cannot do much with the nodal part. The nodal part is going to be fixed. We cannot do anything with that. That's not that the problem, because we know that the linear part is not going to be problematic. We want to deal with this term here in a different way in order to reduce extrapolation. And what we propose is to define a map. Let's say that this is the interior, this is our element, and let's say that we want to extend it to this sub segment AB. And what we do is we create a linear map, let's say from AB to 0, 1, okay? And now we replace our basis, in which instead of having this, now we add S of this. So doing that, we can check that we span the same space, but now we, in the high order part, we never extrapolate, okay? So this is what we proposed, and doing that, we can prove that that this operator here, the extension operator, now we get rid of the k that we had before. We're only extrapolating up to quadratic, no more than that. Okay, and we know that for quadratics things work pretty well, so we expect that this will solve the problem that I told you before. I'm going to talk later on a little bit about how to go to multiple dimensions. It's slightly more tricky, but let's keep it aside for a moment. So for instance, this is order 4. These are the model C0 bases, and these are the Lagrangian bases. This is a standard. And then these are our what we call generalized model C0 bases, in which we are extrapolating with the formula that I told you before, with a mapping from here to here in order to compute the Jacobi polynomials. And with that, you can observe that the difference is quite noticeable. Okay. So now you can see that the effect of the order in the condition number is much smaller than before, and we can go to multiple dimensions working with bounding boxes. It's slightly more complicated. I'm not going to spend much time on that, but the idea is that when you have here, let's say an edge, you can see how far the edge is going to extrapolate using some geometrical computations, and with that you can decide how to define these Jacobi polynomials. Again, I'm not going to get into all the details, you can find it there, but the good thing is that with that now we can go all the way to order 5, which is what we tried there, and we can get the expected results all the time with the right convergence. Okay, so this way we're able to solve these problems for solving elasticity in 2D and in 3D, and in all cases we were able to make our solver work, okay, for different problems here. So yeah, another topic that we were working with is, let's go to time now. We're going to have interfaces, and in that case we want to do something, because certainly if we have something like this, we need to have ALE formulations in order to deal with these movements of the mesh. But then with ALE we have all the issues related to remeshing, etc., when you have moving domains, etc. So what we were considering here is, can we use a space-time embedded formulations in order to deal with these interface moving interfaces. And this is what we did in this very recent work that's, I think, about to be published. And I'm not going to get into details, but it's pretty standard. We can use some kind of tensor product definition in which we only extend for every time we only extend in a space. There is nothing to do in time. And with this, we can prove all kinds of error estimates and stability. Here we have worked on anisotropic space-time error estimates for these formulations, and we get and also prove that the resulting methods are robust. For instance, in this simulation here, we have two disks. This is a convection diffusion reaction problem. We have two disks that merge, and you can see that there is a nice the diffusion starts working when they are in contact, right? And you see that's very smooth on this region. So it seems that it works pretty well. And finally, probably 2 minutes, I wanted also to talk a little bit about geometrical discretization, because all this is very nice, but still, I said at the beginning that I wanted to get rid of unstructured meshes. And I would say that when we work in finite finite elements, most of the time we are working with level sets, right? So it's not really realistic, because then most of the people work with very simple geometries, and then it's unclear whether all this pays the price for complex problems. Usually, in finite finite elements, people work with implicit meshes via level sets, and to make these geometries explicit is a problem by itself, so it's very hard, and we are not going to get into that. What we try to do here is at least to have a framework, a geometrical framework that gets an orientable manifold B that we are going to represent in terms of an STL mesh, a surface mesh, which is something that's much more doable, right? And based on that STL mesh, we are going to create all the integration that we require for our algorithms. Okay, so this is a work that I did together with Perantoni and Frances. Perantoni is my PhD student, and also quite recent work. If you take a look at the equation that we have, both penalty or aggregated FEM, you need to add two complete integrals on the interior and on the boundaries, right? We must be able to have a mechanism that allows us to integrate these quantities. So what we do at the end of the day, I'm not going to get into the details, is to be able to extract some kind of, let's say, a polytopic description of the interior of the domain. Okay, and in order to do that, we have to work with clipping algorithms. We have to work with convexification algorithms in order to make spin convex even when they are not convex, etc., etc. All the details are in the articles. It's quite computational geometry oriented. And I have to say that here the devil is all the time in robustness. When you are in geometrical computations, the hard part is to make it robust all the time. That's the real problem, right? So we learned that the hard way. So after, let's say, quite a lot of work on that, we ended up with something that we consider is extremely robust. We went to the Thingy 10K database and we extracted all the geometries that provided solids. Okay, these are just a bunch of them that we run, like about 5,000, and we apply our integration algorithms on them. The numerical integration, we have different choices. We can use simplification, or you can use quadratures for polytopic meshes, which, by the way, don't work very well when you go to high order finite elements. I think that this is an open problem, but that's another story. And then we, as I told you, we have about 5,000 geometries. And when we started playing here was, let's compute the volume of all of them and see which is the error that we get. And we were able to compute everything, nothing broke down for all of them, and with errors that were very, very low. Then for some of these, you can see here some of the figures that we solved, some of the STL representations of the surfaces for these that were oriented in all cases. And for some of them, we started solving finite element problems for these geometries using unfitted finite elements. And what we wanted was to make it work, to break it down, moving things to try to end up with situations in which something broke down with translations, rotations, etc., in different edges. And we were able to see that, in fact, the algorithms are very robust. It was not that easy to reach that point, but then we were able to solve finite element problems on top of them. And you can see that we expect at some point the expected convergence error. So now we're able to solve problems in geometries that are not that simple with unfitted finite elements. And all these, we don't require any unstructured mesh. All the time, optimum meshes that are very easy to handle. For instance, for sure, you can also do it in both sides. We can solve a fluid structure problem. In one side, with all the machinery, you compute the solid. In the other side, we compute the fluid, and then you can couple them as you like. So all these kinds of things can be done within this framework. We are now working on the nonlinear extension in order to have a CAD representation and work on that. And just to finish, let me tell you that, if I have the time, all these have been implemented in GridUp, which is a finite element framework that we started to develop, let's say, in March 2019, not that far away, together with Frances. And I would say that's probably because it's the first finite element code that's in Julia and that really exploits Julia. It's been very, very successful. Like, people from many places that I don't really know are working and are publishing papers with GridUp, which is something quite nice. And we have an article here. I would say that the short message about GridUp is that it, compared to, let's say, Phoenix, that have these very nice expressions, let's say, for weak forms, but Phoenix requires, you probably know, compilers of the linear forms that they create by their own. So it's very rigid. And what we do is, what we observed was that we had an opportunity with Julia. Julia is just-in-time compilation, and we can just leverage the just-in-time compilation in Julia in order to end up with things like that. And that's one of the key parts of GridUp, is that you can write your problems in such a way that's extremely simple. And you have this high-level API for people that don't want to get dirty and start implementing the loops at the main drive. And the good thing is that everything is written in Julia. It's not that this is Julia and then you go to C++. No, everything is written in Julia. So if you do the finite element, if you want to implement Poisson solver, the Poisson solver here is the Julia, Phoenix, GridUp, UFM, and DL2. There was a previous Julia package, and you can see that the number of lines that you would require here are very small compared to other more standard finite element solvers. And I said the reason is relies on this just-in-time compilation in Julia, which in Phoenix they do it with their own compiler, but this comes with many problems because they have to maintain and extend the compiler for every extension in the high-level API. With regard to time, it's pretty much the same. In this figure, they were pretty close. Sometimes one lie more or less, but Phoenix and GridUp have a very, very similar, are very similar in terms of computational cost. And if to finish, this is a more complicated bilinear form. I think that this is a Fruiter structure interaction with Nietzsche terms. We have jumps, means, etc. And also, with regard to the embedded part, we also have an extension of GridUp in which we deal with all this embedded part that I presented here. Most of the codes are already there if you're interested. And with regard to the geometry, is in this other package that we have here in which we cut all these geometries, etc. You can also find it in GitHub. And just to conclude, today I've been talking a little bit about which are the problems in unfitted finite elements, for those of you that didn't know them. I've been talking about CAD-FEM, about CAD-FEM, and the connection between these two. I briefly covered how we do the integration part, the geometrical part, and the extension to space-time. And I also been discussed how we have been able to solve the issue that we encounter when we go to high order aggregated finite elements. And finally, I made some comments about our software. There are open problems for sure. Now we are working on geometric multigrid for this kind of schemes. I still don't know how to define extensions for exact Durham sequences in unfitted finite elements, so that's something that some people have asked me. I don't know yet. For instance, I don't know how to create point-wise divergent free approximations in unfitted finite elements. There are many things that are not solved, but that's research that's open, and probably if I have the time at some time, I would like to look at. Okay, thanks a lot for the time. I'm sorry that it was a little delayed.
Thank you very much, Santi. I think that you fitted the time perfectly. Maybe you have time for a couple of short questions. Ricardo, please.
Sorry, I'm always the one that asks. But going back to your, I think it was one of the last slides when you were speaking about.
Hopefully, going back is going to be going back to what?
When you were speaking about what you do with STL, I didn't grab what you meant by, I mean, explicit and implicit representation. One is level set, but the other one is, I didn't get it. So,
Level set is an STL mesh. So if you give me an STL,
the other one, the next
one. Yeah, I mean, usually, most of the time when we started working on this, we use level sets. Because in level set, you can use this kind of mounting cubes, not that complicated, right? And for simple geometries, you can forget for a while about the geometry. Yes. But then you have the limitation that you are writing your problem in terms of a level set. So probably that, from an industrial point of view, is not super interesting because many times people are going to come with the, let's say, this is the geometry I want to solve, and I don't think I will be able to present that as a level set.
When you're given the STL, how do you represent the STL on the top of your mesh? Do you have an implicit representation? So do you get a level set out of that?
No. I cannot get a level set of this. No, I don't do that. So what I do is, let's say that you have your mesh. We have certain algorithms that allow me to decide every one of the faces in my STL is, let's say, this is what geometrical predicates that tell me more or less where a face in my STL is going to be located in my background mesh. Okay. Based on that, I work on clipping algorithms in order to cut things. But certainly, if you have something that is not convex, you need to, let's say, convexify your shape with something that's called. When you have something that's non-convex, you need to define what's called. Anyway, so you have to cut it into convex part. You need to process that is convexification. For instance, you can see here, you need to convexify your geometry in order to end up with something convex, and then you need to do clipping algorithms in order to. And we start with, let's say, with square. You start applying all the clipping algorithms, and assuming that's convex, you end up with a polyton. And you can think of this like it's an algorithm that works even for arbitrary dimensions.
Sorry, for example, I see two lines of people doing this sort of things. One was, how was it called? Ranks technique, finite cell method.
Finite cell method
itself. They were essentially placing Gauss points in the right places.
No,
within the.
I don't think that this is that. I think that what they do is.
It's like the shifted boundary method, in which you're telling it's neither of the two.
It's totally different. In the shifted boundary method, what they do is they try to shift the boundary. So they create all these algorithms that try to move the boundary conditions from here, from the real, to that one, but that's another story. That's not what we do. We work with the real geometry, because when you do that,
you're doing a sort of local remesh in a sense.
no, it's just this is nothing but the computation of Gauss points. This is nothing but I want to integrate here, right?
Okay.
And I'm going to integrate here. I'm not going to do anything else but computing exactly, let's say, for polynomial order, whatever, this integral. This is what I'm doing. I'm creating integration rules. Okay, so I'm not doing anything like shift boundary method, which changes the problem, or I'm not doing what RAM is doing, because what RAM is doing is starting for me is like a very brute force approach, in which you start using adaptive main refinement, and you start trying to adapt here. All the time, in general, you're going to make an error, because you're going to approximate it somehow. So then when you say in finite cell method, you go to high order, I don't know, because then the order that you're commuting in the quadrature is of order H, it's not of order.
I'm not defining the method.
No, I'm explaining you. I'm explaining the difference.
So
what I'm doing here is
the
just
integrals
in the interior.
Yes.
I'm creating quadrature rules that compute the exact integral of my polynomials in the interior part, which is all I need for my formulation. And the other one that I do is the integration here on the face. And then I also have to trim, let's say, my boundary into pieces. And that's very easy to say, but the problem is to make it robust. That's what we struggle with for some time.
Thank you. I got the idea at least.
Any other questions or comments from the online audience too?
So you said you have solved problems with mixed problems, right? So have you solved mixed problems with mixed finite atomic spaces? I mean, these are spaces for the variables.
No, this is what we did. If you do stabilization, it's very straightforward, I'd say, right?
The question is, could it be possible that the aggregate is different for the different spaces?
It's not that simple, but yes, it could be possible, but we decided to go another way around, because probably the aggregate, the geometrical aggregate itself, when we're at some point when we started working on this, we wanted to put some constraint on the shape of the aggregates, but we ended up giving up, because that part is something that's impossible to predict. So I'm very flexible in terms of the aggregates. I receive an aggregate and I have to work with that. Okay, so now I have an aggregate for the velocities and for the pressures. But if you do a naive approach, you won't have the in-soup condition, because the in-soup condition is true in interior, but when you extend, it's not that simple how you make it work. So for instance, what we had to prove there was for QK, PK minus 1 discontinuous, right? We were able to find a way to prove in-soup stability for a given aggregated mesh. Okay?
What was it? Let's say the union of the two aggregates, or I mean the union of the aggregate for the velocity and the aggregate for the pressure, or
you have only one mesh, let's say,
yes.
But the mesh has
could
be, but we don't exploit that.
Oh, okay.
Because at the end of the day, the geometrical part is we do that, we receive the aggregate mesh, and we don't try to do anything with that. We live with that. So we have to work at the functional space. And then we realized that we needed, if you don't want to add anything, any kind of stabilization, we needed to do some kind of serendipity type. When you do the extensions, you were not using the total Q space, but the serendipity extension. And with that, we were able to prove the in-soup condition. It was a little bit technical, but so when you do the extension, we needed to, we did like 3 years ago or so, but we needed one way to do it and to prove that you could get, in all cases, an in-soup stable element was working with serendipity finite element spaces at some point and on the cat cells. And with that, we're able to prove that we could preserve the in-soup condition that we have in the interior. So it's very rigid. The proof an in-soup condition is not that simple. And all the time, and related to my last comment, right? We are very flexible in terms of geometry, and we pay the price because let's say things are more complicated. When you are a standard finite elements, you have this polytope, you know, that you have a triangle, you have a bilateral, and then you have this connection between functions and geometry, right? That's essential in finite elements. Here, you need to relax that, and that makes the analysis a little bit harder.
You also talked about the combination of pitches and cut cells. Do you apply a combination of that here in these cases where you work on the STL files? Do you create an octave mesh to better represent the geometry and then use cells, or do you use a pure uniform background mesh?
The good thing of this is that this algorithm is cell-wise. It's an algorithm that is independent for each cell. So you don't care about, when you're in one cell, you don't care about the rest of the cells. The algorithm is, okay, you have let's say a searching algorithm for which we can use a very efficient tree-based search algorithm. But then at each cell, everything is local. You don't have any kind of a global treatment of what we do here is independent of what we do here. And this is the key, right, compared to structured mesh generation, that our computation of the integration rules is local to each cell. Okay, so that's easy to put it in our octree solver. If you ask me whether I have done this work together with octrees, not, because this is a work of my student, and I don't think he's gonna have the time to combine all the two things. But it's a straightforward in the sense that that's a cell-wise computation. So it's not like a finite element solver, or it's not like a linear solver that, you know, when you go to parallel, that's going to be very complicated.
I think I was only confused why you talked about octree at some point, but there was, if you want to do local refinement later on these models, but when extracting all meshes from the STL files, you are not actually applying octree.
You can. What we tried to do in this work was to work on this, right? If you have an octree mesh or not, it's not important, right? In fact, we couldn't even, all these algorithms, you have a starting polytope, and you can start if you like with triangles. It works also in case of triangles.
Yeah, I agree. I was just wondering what you're using for the STL.
No, the only thing that, from a practical point of view, we started working in another code in FEMPAR, and in which we did part of this work till 2018 or so. Then we moved in 2019, we moved to GridUp, and there is still one thing that we have not implemented yet. We have octree handlers. Yes, we could do that too. The only thing that we don't have yet in GridUp is we have the constraints, but nobody has play, let's say, with HL activity. So even though it's there, I'm not sure it's gonna, but there are parts that are missing.
So follow up, because we were talking about constraints that you need in octree meshes, and there are alternatives now. There are several types of elements where you don't need to constrain, but actually have that extra node in the larger element. I was wondering if that would help you, or maybe it actually makes it more complicated.
I have an article on, for instance, HHO, in which we use. I have an article about HHO. You're talking about polytopic meshes, right?
Yeah, polytopic or PNH.
Yeah. You can create this problem, but that's another story, because then you have your announce on the skeleton, then you have your announce inside. Things become much more complicated and much more inefficient in terms of computational cost. So I have a work on HHO in which we work with amphitic finite element. There is not the concept of amphitic, because it's like what I said in DG, right? In DG, you can easily work with polytopic meshes. It's not a problem. And with HHO, HDG, you can also deal with that. From a geometrical point of view, they are very flexible, but then they have other issues too.
But I was still talking about quadrilateral elements, just with the extra node that you don't need to constrain.
I think that we can discuss it later if it's okay for you, and maybe your question can be delayed after the seminar, okay? Because it's quite late now. So let's thank Santiago again. We'll see you in the next session. Bye.